Okay, cool. So hi everyone. I'm Akif. So today we talk about binary search. And so the one thing I want to mention first that the way that we have this set up is that there's sort of two very interrelated topics here. The first is just using the built-in binary search in C++ and what situations you would use that in and how to do it effectively. And the second is actually writing your own binary searches and and recognizing when problems have that and how to use it. Okay. So I'm going to start off with just a bit of a recap from the C++ STL lecture. And there, if you guys were there, we talked about lower upper bound, which was the built-in binary search functions. Java has something similar, I think, but yeah. So just to recap, upper bound, if you give it a range in an array or vector or something, and you give it a value, x, let's say, upper bound gives you the first index in the array where the value is strictly greater than x. And if there is no such value, it gives you one past the end of the range, which is in this case just be n. Yeah, index n. So in lower bound is a very similar thing, except it gives you the first index where the value is greater than or equal to x. And same thing where if you go out of, if it's no such value, then it just gives the end of the range, one past the end of the range. Strictly speaking, this doesn't give the actual index. It gives an iterator or a pointer into the range. So you have to subtract out the beginning of the range to get the actual index. So in this case, it would be upper bound this minus a would give you the actual index value. Or for vectors, it would be minus your vector dot begin. As you would expect, this only works on sorted arrays. Because of that, it only takes log n time, as binary search does. And one thing we mentioned was that for sets and maps, you can't use this thing because sets and maps don't have random access iterators. You actually have to use the sets dot upper bound function or dot lower bound function if you want to do that. Okay. Any questions or anything? Okay. So here's our first example problem on using upper bound, lower bound, and it's called finding zero. So you have an array of integers, let's say of size up to 1 in the ninth, 10 in the ninth, and the array is maybe 100,000 long. And you need to answer either yes or no whether you can find two elements that add to zero. So an example here, if you're given this array, the answer is yes because you can use 5 and negative 5. Okay. So yeah, any ideas for this? How you can use binary search for this?
We can, let's say for each number, we can find if there is, so let's say for 5, there is a -5 present. We can do for uh, every
Right.
such element if the array is sorted.
Right. Yeah, exactly. So the trick is to first sort the array, exactly as Nachiket said. And then you just loop over the array, and for every one of those elements, you do a lower bound to find whether negative of that exists. And so the way you do this, you just check whether the lower bound value of the negative, to check if a value exists using lower bound, all you have to do is run lower bound on it and check if it equals that value once you dereference it. So this syntax here is, the star here just means to dereference if you remember, which means get the value at that pointer or iterator. And the reason this works is because I said lower bound finds the last guy who's greater than or equal to you. The first guy is greater than or equal to you. So if there is one that's equal, when you dereference it, it'll be that value. And so maybe this is slightly more clear if you look at the code. So we sort the array or vector or whatever, sort the vector. And this is using the a macro from the STL lecture, which just is a short form for dot begin and dot end. Then we loop over it, and then we search in that thing for negative x using lower bound, and then we dereference it to get the value and make sure that it's equal to the value we're searching for. And if that's true, then that value exists, and we print yes and exit. Otherwise, it's no. Any questions? Okay, let's keep going. Okay. So now we're gonna shift away at least for the time being, away from lower bound, upper bound, and more onto just general idea of binary search. Okay. So binary search in general, you have some sort of Boolean function, f of x, on integers. Okay. So this is a function that takes an integer and returns it true or false. And we usually call this a predicate. Yes. Okay. So this one, right? The all macro. So all this stuff is all recap from the STL lecture, but if you want the actual macro just itself, I can give that to you. It's this. Let me copy and paste it. Yeah, it's this macro. So it's just to fill in for dot begin, dot end. Yeah. Okay. Yeah. Okay. So yeah, in binary search, we have this function which we call formally the predicate. This is also sometimes often called the works function informally. And this predicate, to able to do binary search, need to have this specific property called monotonicity. Monoticity. It has to be monotone. What this means is that it has to be false for a while. If red, so if you look here, red indicates false and green indicates true values for f. So it has to be false for a while, and at some point it has to switch and become true forever, or vice versa. It could be true for the beginning and then false for this side. And the whole goal of binary search is to find this switchover point where it goes from true to false. As an example, so you can see how this relates to the more traditional idea of binary searching for a value in an array, that's just equivalent to using your predicate, making your predicate f of I be the Boolean function whether ai is less than or equal to x. Because if the array is sorted, right, ai will be less than x for all this part, and at some point, once you reach ai, it'll be greater than or equal to x. And then equal to here maybe, and then greater than from this point onwards. Or if it doesn't exist in the array, it'll just straight over switch over to being greater than x, and this whole green part will be strictly greater than x. And so this predicate is what gives us our traditional binary searching in an array. So now I'm going to talk about one way to implement binary search by yourself, and it's called the invariant binary search. And it's my personal favorite, and I think it's very intuitive and nice to use. And it avoids a lot of the issues with other binary search formats. So the idea with invariant binary search is that you have two pointers, and you maintain them. And initially, one of them starts out as in the always true zone. So you make sure that at the beginning, one of the pointers is always true. It's always pointing to a green element. And that the other is always starts out pointing to a red element, a false element. And the key here is that you make sure that this condition always holds. That this guy always points to false, and this guy always points to true. And this is what the invariant binary search means, that you maintain this guy's always false, this guy's always true. And basically what you do is, while maintaining this invariant, you keep shrinking these guys together. You keep putting them closer and closer. Eventually, if you maintain this invariant, when they meet, you'll have found the switchover point. Because this guy will be red and this guy will be green, and they'll be right next to each other. So that was a pretty general idea. Now I'm going to show you some pseudocode to explain this better. So here for example, L could be this very negative value all the way to the left, so it's always false, using this model where it's false and true. Right could be this very big value, which for some reason is always good, is always green, is always true. And what you do is you keep looping while they're at least two apart, while they're more than one apart, the 2 pointers. I guess I didn't mention, these are your left and right pointers, L and R here. Okay, and then so when you do this, you calculate their midpoint here. You calculate the midpoint, M is R plus L over 2. Okay, and then you run your predicate function, your works function on this midpoint. And if this worked, right, then you know that you can move your right pointer to M, because the whole point is that you're shrinking it and making sure your right pointer always points to a green value, a value for which your predicate works. And so if it works, if your midpoint works, then you can just move your right pointer to it, because it'll maintain the invariant. Otherwise, you know M doesn't work, so it's a red element, so you can move your L to it and shrink it that way. Okay. Any questions on this?
Could you explain why L could equal M?
Right.
Like
so
in the else?
Yeah, so in the else, right, we know that M doesn't work. That works M is false, right? So in that case, M is one of these red elements. And more than that, it's closer. It's more towards the middle. It's somewhere in the midpoint of your right and left, right? So you can just move your left, because remember the whole point of the invariant is that your left needs to always be pointing at a red element. So you could just, so if M is a red element, which is what this else means, you could just set your L to M and keep it a red element and shrink the things together.
Okay, thank you.
Yeah. Okay, yeah, and then when you're done with this while loop, your R and L will be at the switchover point, and you can use whichever one you want, whichever one you care about. Okay. So here's some important points to mention. So first off, since this whole while loop condition is that R minus R and L are more than 1 apart, it'll always keep shrinking while you're in the loop. You don't have to worry about it, unlike normal binary search, which you may have seen, you don't need to worry about floor division versus ceiling division. Whether you can use R plus L plus 1 over 2 or R plus L over 2 doesn't matter. It'll always keep shrinking, and you'll never have an infinite loop type thing at the end, no matter what you do. The next point is that you can do the exact same thing except have L be green, L always be true, and then R and then the right pointer always be false. It's the same thing. You just have to flip the if statement. And then works will mean L is the thing that works and R is the thing that doesn't work. The other very nice point is that the original L and R never get works called on them. This is slightly harder to see, but if you trace it out, if you just sort of trace it down in your mind, you can see that this is true. So even if it's possible for your array or your setup to be all green or all red, it doesn't really matter, because you can just use a value that's 1 out of bound, just 1 out of bound either to the right or the left, and make that your original L or R. Make that sort of, because you can just pretend that they're always true or always false, and your works function will never be called on them, and it'll just work fine. Any questions on this? No? Okay. We'll see more examples of this stuff as we go on. Okay, time complexity. So in the pseudocode, as you saw, we always shrink either L or R to the midpoint. So the range basically cuts in half every time. And since the range starts out as whatever the original size of your array or setup is, it takes only log n complexity before your L and R meet at the switchover point. So this is very good. Right? Log n grows very slowly. So if you have a range of, let's say, 1,000,000, log of 1,000,000 is only 20. So it'll only take 20 steps to finish this binary search, even with 1,000,000 elements. That's why this is so powerful to use in competitive programming and programming in general. Okay. So now let's go and use our earlier example of search in an array and try to apply this invariant binary search to it. Obviously, when you actually code, you would just use lower bound or upper bound for this, but it's good as a teaching tool right now to show you how this relates. Okay. So as I mentioned earlier, we'll make our predicate be f of I be ai less than or equal to x if we're searching for x. Then L will be the last thing that's less than or equal to x, because that's the last thing, when you're done with the binary search, when you're done with the loop, will be the last thing that's less than or equal to x, because that's the last green element. And R will be the first thing that's greater than x. It'll be the first red element. Right? So when we're at the switchover points, it'll be like this. So as an example, if you're searching for 8, your left endpoint will be the last element that's less than or equal to 8, and your red endpoint will be the first one that's greater than 8 here, the switchover point. And so to check whether or not x is in the array, all we need to do is check whether AL equals x at the end. Because in this example, let's say 8 is in the array, as you see here. So the last element that's less than or equal to 8 will be equal to 8. So, and that'll be the left endpoint, right? But if, for example, this was, let's say, I don't know, 7, right? Because 8's not in the array. then the situation at the end of the binary search will still be the same, except when you check AL, it won't be 8. You only have elements that are less than or greater than X. You'll never have anything. So here's the code for the array search. It's pretty much the pseudocode before, except we wrote a natural code and used the concrete works function. So here, here's one of the example of using an out-of-bounds value I mentioned earlier. So, because for example, it could be that your entire array is less than or equal to 8, or your entire array is strictly greater than 8. So you don't know for sure if you have any values that are always true or always false to start out with. So as I mentioned, you can just use values that are 1 out of bounds. So if here, use -1, because that's just 1 to the left. That could, 1 to the left of anything that could actually show up. And same thing here. This is 1 to the right of anything that actually show up here. So these values are sort of, you pretend are always true or always false, and it just works. Then you have the while loop condition. You find the midpoint, and here's the works function, the same a to am less than or equal to x. And if it works, then you set L, because L is the one that stays green. You set that equals M. Otherwise, you set R equals M, because that's the one that always stays red. And at the end, you check whether or not AL equals X. One tricky point here is that if everything is strictly greater than X, right, then your left endpoint at the switchover point will be sort of here. It'll be a position -1, because that's the only thing that can stay green. So you need to check that first to make sure that didn't happen. You need to check that L does not equal -1, and that it's actually equal, that the value there is equal to X, to make sure this works. And if this is true, then you have X in your array. Otherwise, you don't, and that returns false. Any questions on this? Yeah, you know. You can unmute yourself.
Oh, it's Caden. I didn't say my name right. Okay, so my question is that why don't we set L to 0?
Because as I mentioned, you're not guaranteed that that 0 is always green. If let's say the first element here was 10, right?
Yeah.
Then your invariant is broken from the very beginning. So you didn't make the sort of fake value in this case.
Yeah, and then in the end, we can just check if AL equals like the element that we're looking for.
Exactly. Yeah.
Yeah. So in this case, I think you could set L equal to 0 and it wouldn't break anything.
Oh, that's what you meant. I see your point. Yeah.
Yeah, but in general, that's not a great thing to do because there are cases where you can't do that.
Okay.
But yeah, in this case, it would work.
I see your point. Yeah, that's a good point.
Yeah, at least off the top of my head, I can't think of anything that didn't work. If you set L to 0, yeah.
Yeah, that's a good point. Nice. Okay. Okay. So next example we're gonna do is the square root problem. Okay, integer square root. Okay. So the problem here is that we're given a number and we want to find its square root if it has one. Okay. So what we're going to do here is we can make our predicate be whether or not m times m is greater than x. So then r will be the first thing which its square is greater than x, and L will be the last thing with a square less than or equal to x. For example, here, if we're trying to search for 25, we're trying to find the square root of 25, you can see here that index 5 here is the last thing with square less than or equal to x, and then here 6 is the first one greater than x. And in this case, 25 has a square root, so it'll be actually equal to 25 here. But conceivably, if you had, I don't know, 28, this would be the same situation, except it wouldn't be equal to 28. You know? Does that make sense? Okay. Now let's keep going. Oh. Nice. Okay, let's keep going. Okay. So as I said before, as we did in the last problem, it's pretty much the same thing. It's very formulaic. We just replace the works function in our setup, and that's all really we have to do. So here, L starts out as 0. So we can make L 0 here because 0 is always guaranteed to be less than or equal to any positive integer. I mean, 0 squared, which is also 0. Here, we can just make R like x plus 1 because x plus 1 squared is also guaranteed to be bigger than your square root of x. And yeah, when we do our loop, find the midpoint, check whether it works. If it works, it's a green value, so that's R, right? So we set R equal to the green value. Otherwise, it's left, the red value. So we set left equal to the red value. And then we're done. We just check whether or not L squared, which is L squared is the only thing that has the potential to be our square root here because it's the last thing with square less than or equal to x. We check whether or not that value squared is equal to x. If it is, then we return it. That's a typo. That should be L. Sorry, that's a typo. That should be return L there. Otherwise, we return -1 because it's not a perfect square. Okay.
One thing to notice with this problem is that we don't have the actual array like we did in all the other problems. The array is like, you can think of like you have a really long list of all the square numbers, but you don't need to actually generate that array for this to work, right? So what that lets you do is you can now binary search for x's that are much bigger. So for x's that are like 10 to the 18th or whatever, even though you can't generate a list of all the squares up to 10 to the 18th. I don't know if there's a better way of explaining that, but like you
No, I think that
kind of
explained
get
it
to
well.
binary search without having the array in place there.
Yeah. No, I think that's a good explanation. Yeah. Yeah, often in a lot of binary search problems, there won't be an explicit array, and you won't be able to compute one, and that's sort of the strength of binary search, where you avoid making that. Okay, let's keep going. Oh yeah, so this is sort of a aside, but we want what happens if you want to find the square root even for non-perfect squares, even if you want to allow for non-integer answers. So for example, square root of 2 here is like 1.414 whatever, right? So first of all, we can't store it with perfect precision because it's an irrational number, so you're always gonna have some error. But let's say we need it within some epsilon. So here we have 10 to the minus 6 of the actual answer. But how could we modify our binary search to solve this? Any ideas?
So once we reach a particular point, let's say in the array where we have narrowed it down to those two elements, we can take the square root of those two elements, and the value would be somewhere in between those.
Right, but we don't. It's not good enough to find just those two values because they'll be at least one apart, right? So we need the answer to within a millionth here, let's say.
So this is a problem where you really can't construct the whole array. I don't know how to give a good hint for this.
Yeah. Okay.
Yeah.
Exactly. Yeah, Abdul got it. Yeah. So it looks very much similar, except instead of being r minus l greater than 1, we just make it in some small epsilon. And we all obviously also use floats, LDs here instead of LLs. So yeah, we make them floating point things, long doubles we always use instead of integers. And then we just do while r minus l is greater than epsilon. And you can, and because you want the hold on, why is this a thing? Was your problem set up that the answer had to be, like the square had to be within 10 to the 6 or something? And negative 6?
I don't know. I mean, either way, it's good to go overkill on epsilon. That was
Yeah,
kind of my point.
Yeah, that's a good point. Yeah. Binary search won't always. You can just, because binary search is so fast, you can just always up the epsilon to a very small value, and it's perfect.
Yeah.
Yeah. For LDs, 10 to the negative 12th is pretty standard and good. So you can see here, the rest of the code just looks the same here. So we just have to use the epsilon here and use floats. And here, L and R are so close together that it doesn't matter which one you return. They're both within epsilon of each other, probably hopefully less than epsilon within each other. So you can just return either one, and it's fine. And so the runtime here will be log x over eps. So you can think of it as you're sort of doing the normal binary search to get down to within 1, and then you're doing another sort of binary search to get down within eps. It's the same binary search, but in terms of precision. That's one way you can think about it. Sort of. I don't know if that helps. But the good part is that this doesn't really matter that much, because even if x is 10 to the 18th and you're doing 10 to the 12th, this is only log 10 to the 30, which is only 100 steps. That's great. And sort of another fun fact is that you really don't want to do more than 100 steps, because it's not any benefit to you, because you sort of can't, depending on how big your values are versus how much precision you need, you'll never be able to sort of have more than 100 steps worth of actual useful precision in it to be stored in the float. The sort of mantissa part of your float type will not have more than 100 steps of precision of storage. So alternatively, instead of this while loop, you can even just write a for loop and just do for I less than 100, and that also just works. And it's all that's good. But this also works just fine too. Any questions? No? Okay, let's keep going. Okay, so this is our first actual problem. It's called, I guess, with this invariant binary search stuff, it's called magic powder. So you have a cookie recipe with n up to 10 to the 5th ingredients. And in this recipe, it tells you that you need AI grams of the ith ingredient per cookie, and AI could be up to 10 to the 9th. But you have bi, which is less than or equal to 10 to the 9th grams of the ith ingredient at home. So in your kitchen, you have bi of it. But you also, in your kitchen, have K, also up to 10 to the 9th, grams of this magic powder. And this magic powder can be substituted for any other ingredient. So 1 gram of magic powder is used for 1 gram of any other ingredient. And the question is, how many cookies can you make? What's the most amount of cookies you can make? For example, here, if the recipe says you need 2 of ingredient 0, 1 of ingredient 1, and 4 grams of ingredient 2, and you have 11, 3, and 16, turns out, and you have 1 gram of magic powder, it turns out you can make 4 cookies here. Because what you can do is you can take this magic powder, use it on the second ingredient, and then you have enough for 4 cookies, because 2 times 4 is 8, which is less than 11. 4 times 1 is 4, which with the magic powder is works here. And then 4 times 4 is 16, so you have enough for this one too. Okay. So any ideas?
Wait, I have a question.
Yeah.
Could you use the magic powder on more than one ingredient?
Yeah, you can separate. You can use 1 gram at a time
okay.
and separate it as much as you need. Yeah.
So I guess the key to this problem is think about what kind of value you can binary search on and get a useful answer, because it's not as clear here as it is in the problems we've done so far.
So would you want to search for the value where when you divide B by A, you get the smallest amount?
That works, I think, without the powder, right?
Yeah, but then like you have to figure out which ones to use the powder on.
Right, but your thing doesn't really work for the powder because maybe that one has a high AI cost. So then adding the powder will just be useless and it won't actually get you to that next cookie.
No, I mean,
Whereas,
that would work. Like you're basically adding to the one with the minimum ratio of B to A. So that would work. The problem is the runtime. Because you have like 10 to the 9th grams of magic powder.
oh, you're saying do it every step. That works. Yeah.
Yeah.
Right. Yeah, I see. That's a good point. Yeah, but it's the runtime. You can explain.
Yeah, so if you have like 10 to the 9th grams of magic powder and you try to add them one at a time, like to the smallest one as you keep updating, that'll run out of time because you have like 10 to the 8th operations. So
Yeah, I feel like with these, I have like the problem where I always tend to come up with the most like brute force solutions. Like not just with
Yeah.
this one, but with everyone.
this problem, yeah, everyone comes up with really convoluted brute forces for this, like specifically this problem. I remember doing that.
As Joe said, this lecture is about binary search, so keep that big picture in mind. And yeah, as I said, try to think about what you can even binary search on. There's not that much.
The actual solution is really nice.
Luckily, we have time, I think, so we can give you a lot of time to think about it.
Yeah.
I think Abdul mentioned
Exactly.
yes. Yeah. So, can you think of how you would do that? How would that? How would binary searching on the number of cookies help you? Anyone else? Yeah. Think about how would that work. So if you're binary searching on the number of cookies, right? What's your works function first of all? Can you formalize that first? We should have had a middle slide with this.
Yeah.
But yeah, anyone? I mean, the answer is pretty obvious. Just shout out what if you can even type
Well,
out. Shout
I
out.
don't know.
Well, no, I'm not saying like how to compute it. I'm just saying what the function even is. Like if you can
Okay.
even in English, just say what the function is. Like first off.
So basically, the idea is like given some number.
think-
Oh yeah, go ahead.
I think so. Once we fix on one number, and then we can. Do you think we can iterate over like the array to see how many ingredients we need, and then we look at the k if we have sufficient amount of magic ingredients,
Yeah, exactly.
and then
That's
just
exactly
keep the process.
Yeah, that's exactly right. So as Abdul said, we're going to binary search on the answer. So this is, thing aside, this is a very common sort of theme in competitive programming, where when you're using binary search, I think like at least 7 times out of 10, binary search comes up in the context of actually binary searching on the literal answer to the problem.
Yeah, any problem of the form, like find the minimal value where this happens, or find the maximal value where this happens, that's mostly going to be binary search.
Yeah.
Not always, but
So we're gonna actually binary search on the actual answer to the problem, which is the maximum amount of cookies we can make. So, and then as Caden said, if we fix the amount of cookies, so let's say we call it M based on binary search, let's say we're making M cookies, we actually know how much magic powder we're going to use, because we can loop over the ingredients and say for this ingredient, if we're making 10 cookies, we need this much. We need BI times 10, AI times 10, right? But we only have BI, so that means we need this much magic powder, right? So to be able to do 10 cookies, let's say we can calculate how much magic powder we need. And then our predicate is very simply whether or not we have that much powder in our K value. So then if we do the binary search, the left side will be green, right? It'll be the true ones, the ones you can make that many cookies, and then eventually it'll become you can't make that many cookies.
oh yes, yeah. You can split up the magic powder however you want. Like you can give any number to any.
I'm not sure if that's what he's asking, or he's asking you can reuse the grams. You can't reuse the grams. Think of it, the problem statement itself said it like you can transmute each gram of magic powder into 1 gram of the specific ingredient you want. So you can split it up among different things, but you can't reuse each gram. That makes sense.
Yeah, the idea is you find out how much you need for each ingredient, and then you add those up over all ingredients.
Yeah, so that's you get the total amount of magic powder you need for that setup, for that value of M. Okay, good. So then, so as you see here, for example, for these amount of cookies, for 0, 1, 2, 3 cookies, you need no magic powder, maybe, depending on your recipe. And then maybe for 4 cookies, you need 2. For 5 cookies, you need 4 magic powder. For 6 cookies, you need 7 magic powder, let's say. For 6, you need 10, right? 7, 8, however many cookies this was, I don't remember. I can't count. How many cookies this is, you need 10. So if you have 8 grams of magic powder, you're going to go in here in the middle, right? Your switchover point is going to be here. So the last thing that works is your L pointer. So then the answer is going to be you can make 0, 1, 2, 6 cookies, right? So that's the last one that's less than or equal to 8. And as Joe said before, the whole advantage here of binary searching on the answer or binary search in general is that you can't make this array. This array you cannot compute this whole array of how much magic powder you need for every value of the cookies. But if we sort of implicitly think that this array somehow exists platonically in the universe, then we can binary search on it using invariant binary search, and only compute these values for which we actually have the pointers at, and we need to compute the work function. And only log n of these computations will we find the switchover point.
And how to generate this array? I mean,
you don't. I just, for example's sake, I showed you the whole array here, right?
Okay.
But in reality, in the code, you cannot compute this whole array. It just exists as an actual array in the universe, just in your mind, but you cannot actually compute it in time. So that's where binary search comes in, where we just shuffle these pointers around and squeeze them together. And whenever we need to call the works function, we do compute that value of the array. But we only compute log n values of the array before we find the switchover point.
Right, because the idea is like for your first midpoint, right? Let's say you recurse on like the left side of the array. You never have to access anything on the right side there. So you don't have to like compute any of those values because you're never going to need them again. And then like the same thing, as you recurse, you're sort of throwing out half the array, and those are all values that you don't have to compute now. So you sort of only compute the values you need to compute, and that'll be only like O of log n of them.
If you're speaking strictly formally, like there doesn't even have to be an array. You don't have to even talk about integers or numbers or anything. Only the indexes have to be integers, but the values here don't have to be integers at all. You just have some function f of I, which takes in an index and returns true or false. There doesn't have to be some sort of integer or float array in general at all. And Abdul had a question. You find the amount of activity by iterating through A, B, and doing like Well, not quite. You have to so if you're making M cookies, right? You need AI times M because AI is per cookie in the recipe. Remember, so you need AI times M of the ith ingredient. So you do AI times M minus BI, and that gives you how much magic powder you need to apply for that ingredient if you're making M cookies. That makes sense? Yeah. Okay.
And also, you want to take the max of that with 0, right? Because if you already have enough, then you don't need any more.
Yeah, I think we have code in the next slide. Let's go over that because I think
That's good.
Probably more specific, more concrete. Okay.
Mm-hmm.
So we start out with L equals 0 because you can always make 0 cookies. So it's always going to be green. And then we make R some ridiculously large value, say 3, 9, because even if AIs are 1 and you have K equals 1e9, whatever, this is always going to be impossible to make that many cookies. And you do your binary search loop. You find the midpoint. And now the works function is a lot more involved than it was in our previous sort of problems, right? So we actually have some reasonable amount of code for this. So how does this code work? So this powder variable will hold how much powder we need to make M cookies. Then we loop over all of the ingredients from I equals 0 to n. And then we, as Joe wrote out, we do this max of AI times m minus bi is 0. So again, just to remind you, AI times m is how much of the ith ingredient we need to make M cookies based on this recipe of A. Bi is how much we have, right? So AI times m minus bi is how much extra we need. And if we don't need any extra, then this value will be negative. So we just max it with 0 to say that we can't have negative powder. Powder can't give it back if we have extra. And then we go through this for all the ingredients, and then this is the actual works function. If we have enough powder, which is if powder less than or equal to K, right? Then we're in the green zone. So we set L equals to M. Otherwise, we're in the red zone, so we set R equals to M. And then when we're done, we're going to be at the switchover point, and L is going to be the biggest thing that works, that satisfies the predicate. So we just print out L. One small caveat here is this line. And the reason we need that is for potential overflow. So if your M value is big, somewhere on the scale of 10 to the 9th, and your AI values are also on the scale of 10 to the 9th, let's say, then this AI times M might be on the scale of 10 to the 18th. And then if you do this across 10 to the 5th ingredients, then you have somewhere around 10 to the 23rd. Your powder value will get up somewhere around 10 to the 23rd, which will overflow along. Luckily, this is not that big of an issue because you're never going to have 10 to the 23rd magic powder, right? K can only go up to 10 to the 9th. So if we get above 10 to the 9th, if you have more than K powder needed, we may as well just make that K plus 1. It doesn't matter if we need K plus 1 or K plus 2 powder. Both of them are still in the red zone, and we don't really care. So we may as well just, if this starts getting big, we may as well just min it with K plus 1, because it's still a bad value. This sort of goes hand in hand with we're not actually computing this array. We're just binary searching formally on the predicate, because we don't even compute the actual array here. We're computing some screwed up version of the array where anything bigger than K plus 1 is set to K plus 1.
So we will start from calculating 0 cookie to higher values. So essentially, we are just looking at the lower half of this imaginative array, right? We are not really.
No, because we're not computing it sequentially. The whole point of binary search is that we sort of jump around. So that potentially, right, if your left pointer is here, right pointer is here, maybe, it could happen that your midpoint falls in the red zone. And when we do that, this thing will compute to false, right?
Oh, okay.
And then we will have to bring the right pointer in to the left.
Yeah. No, I understood now.
Okay. Any other questions on this? Okay. So this is our last problem. This is quite a bit harder, I think, than the previous ones. And one hint here for this one is that this sort of is nothing to do with the invariant binary search. I mean, not nothing to do, because you can always implement the other thing with the invariant binary search. But this is more of the lower bound, upper bound type stuff. So think about more less how to implement the binary search and more how to apply it here. Okay, I just put it at the end because it was really hard compared to the other one. So and that's why I didn't put it with the other lower bound problem. But anyway, okay, so we have a piece of timber of length L. L up to say 10 to the 9th meters. And you can sort of think of having marked off positions once every meter from 0 to L. So you can see here, right? This is 9 meters long. We sort of marked off every position, from starting from the left, one at every meter. And you get 2 times 10 to the 5th queries up to. And so there's 2 types of queries. Type 1 has you make a cut at position X, and X can be from anywhere from 1 to L minus 1. So it has to be an actual cut. You can't sort of cut at the edges, but anywhere from here to here, you can make a cut. So here is an example. After cutting at X equals 4 and X equals 6, you cut these 2, and you get these sort of 3 pieces. When I say cut, it cuts in like 2 separate pieces. Yeah. And then the second type of query is you want to print the length of the piece containing position X. So again, from X goes from 1 to L minus 1. So here, if you had 2, after these cuts are made, let's you query 2, this would be, you would print out 4 with it. Yeah, 4. And then for example, if you queried 5, then you print out 2 because this piece has length 2. Or if you queried 8, you print out 3 because this piece has length 3. Okay. And finally, you are guaranteed that the X values are unique across all queries. So you won't be making a cut twice or querying, let's say, at position 4, querying at a cut. And what does that mean? So you don't have to worry about little weird cases like that. Okay. So yeah, any ideas? So any observations and stuff would be just shout them out or type them out. Yeah. You're not, so don't think about the invariant binary search type stuff. Think more about just search the actual like array search type of binary search. Abdul got it exactly, almost. So what would you be binary searching in? This is this last part, just to see if you guys can get it. What would you be binary searching in? How would you set up the binary search?
Would you want to do 2 binary searches, one for the upper bound, one for the lower bound?
Yes, yeah.
And then you can subtract them to find the length.
Right. My sort of point, that's correct. My sort of point was, how are you setting up the binary search? Because for binary search, you need some sort of sorted data structure, right? You need to have them in order. And as you make type 1 queries, you need to somehow maintain your cuts, right? But when I say lower bound, upper bound, there's a function, built-in function C++ that I was talking about that actually does a binary search and gives you those. I'm not sure what you mean exactly. Does that answer your question? Right. No. Okay. So
Yeah,
that's what.
like what data structure.
Oh yeah. So that's what I was asking for you guys to figure out. Also, how would you do that? Yeah.
Well, you have the like X position of all the cuts, and then you also have like the 2 endpoints.
Right, but you can't resort an array every time, right? Because you can have a type 1 query, then a type 2 query, then a type 1 query, and it's back and forth, right? So what do you do? I think that's what Abdul was asking also.
If you guys were here for last week's lecture, the data structure we talked about there are going to be helpful. The problem with that is it's not going to be sorted as you do all the queries.
Yeah. Push back literally pushes to the back, right? You can't push back to a specific location in the array, right? You have to push back to the end. And as Joe said, that'll make your vector of cuts not sorted, so you can't binary search in it. And then if you resort it every time, that'll be n log n per query, which will be n squared log n, which is too slow.
Adam said sec tree.
Insane.
Yeah, exactly.
Yeah, yeah, exactly. So the whole point of set is that you have this sort of dynamic data structure which you can add and check if it exists and keep sorted. And that's very helpful for these types of stuff. So I think that's the whole solution then, I guess. So we maintain the cuts. We keep track of all the cuts so far in a set as we go through the queries. For type 1 queries, we just add them to the set and do an insert. And then for type 2, the length of the piece is given by its two closest cuts. So closest to the right minus closest to the left, right? Because if you look at the picture, for example, if you put 5, it'll be this guy minus this guy, closest to the right minus closest to the left. And as Abdul and Kane figured out, I think, no, it was Joshua, sorry, not Kane. Joshua figured this out. Upper bound gives you the closest to the right, and lower, and then minus upper bound gives closest to the left. So you guys were slightly wrong on that, that the lower bound doesn't actually work here, because lower bound is the first guy greater than equal to you. But you'll never have anything equal to you because the query values can never be repeated, right? So upper bound and lower bound will get the same value here. That's not what you want. You want upper bound and then the one to the left of upper bound. Yeah.
Yeah, so the minus is basically just moving that iterator one position to the left.
Yeah.
So minus of upper bound is the last element less than or equal to x.
Yeah, so that's what that gives. And as I mentioned, upper bound and lower bound doesn't really matter because you know the query hasn't been cut before. Yeah. Any questions? Oh, and then the other thing is that someone mentioned this, I forgot who, but you need 0 and L. You need the endpoints to be in the set already, because they sort of are cuts in the sense that if you query here, let's say the left guy will be this guy maybe, but then the right guy has to be the endpoint, which will never be an actual cut. So you need to have that in your cut set. Same thing with 0 here. Yeah, makes sense. Okay. Well, that's it for today. These are the two actual problems we did. If you want to try coding them yourself. Codeforces has a bunch of binary search problems. This is a link to the whole problem set. Oh, sorry, here. Yeah, so upper bound works on any range of iterators you give. But it has to be random access iterators. So for arrays and vectors, that's perfectly fine. For sets, you have to do something kind of special. Let me go back to the beginning. Because sets don't technically give you random access iterators. So you need to use your internal dot upper bound function like this, you see, or dot lower bound function. Same thing for maps. Does that help? Yeah, but for vectors or arrays or anything that has random access iterators, you can just pass the things into upper bound, lower bound, like here. Okay. Okay, yeah. So Codeforces has a bunch of stuff on binary search. This is a link to the whole problem set for binary search. You can just start at your rating and just do problems there. It's very helpful. Like, these are very nice problems. I think binary search is always very pretty.
There are a lot of problems that have that tag that basically have nothing to do with binary search.
I think it's because you solved with binary search, but you don't have to, or something like that. I think it's also there's a DP and a binary search greedy.
Yeah.
But yeah.
Also, we do have a binary search contest up on the Codeforces group. That'll be up until next week. So you guys can do those problems.